Hello everyone, my name is Gibson Carter. I will be presenting our research on stance conditioned modeling for rumor verification. Here is a small bio about me. I received a bachelor's degree in information and communication technology from Zuzu University in Malawi. That was in 2018. And I got my master's degree in computer science from the University of Arkansas, Fayetteville, USA in 2022. Then in 2023, I joined the University of Arkansas as a doctoral student in computer science, and I'm also a graduate research assistant in the electrical engineering and computer science department, and I am working under the DART project with Dr. Coach. Our research interest lies in the application of deep learning techniques and pre-trained language models in natural language processing tasks. So we use pre-trained language models like BERT, Roberta, GPT. So we use these in tasks like sentiment analysis, stance detection, and rumor verification on social media. Additionally, our research interest lies in leveraging these contextual word embeddings for personalized information retrieval. And so far, we have managed to publish a number of works in different venues in these particular areas. The rest of the presentation will flow as follows. We will start with the motivation, then we will talk about our approach of this work. We will talk about the experiments. We will discuss the results of the experiments. We will delve into the conclusion, and lastly, we will discuss the limitations and direction for future work. A rumor may be defined as a statement whose truth value is unverified or deliberately false. Now, the exponential rise of social media platforms such as Twitter, which is now renamed as X, Reddit, Facebook, has fueled the rapid spread of misinformation and rumors. So this makes the task of rumor verification a critical challenge on these social media platforms. Traditional rumor verification approaches primarily rely on transformer-based language models, such as BERT, to analyze textual representations of posts. However, these methods often truncate conversational threads due to sequence length constraints and overlook valuable discourse signals such as stance labels that reflect user perspectives on rumors. So the traditional approach to rumor verification is just to take a post which a person has posted on social media platform, the source post, and then try to use these techniques to detect if that one is a true rumor or it is a false rumor. Others, they take the source post and also they try to leverage the replies which people are giving toward that particular source post. So the reactions and the stances which are in those particular reactions. Despite using the reactions, but most of the work, they use pretend language models, and because of the length of those replies, it's hard to use every single word in those replies into these particular pretend language models because of the limit of the sequence length which these pretend language models can accept at once. So because of these two reasons, that is, some models failure to use replies, which are stance signals in the conversation thread, and the truncation of the conversation thread. So this has given us a motivation to propose a sequential stance aggregation mechanism that accounts for temporal ordering of replies and chronologically embedding stance labels using a bidirectional LSTM. So we are proposing a solution that is going to aggregate every reply embedding based on the stance type, and then we are going to add this reply embedding to the source, or these aggregating reply embeddings to the source post embedding, and then we're going to model the stance evolution in the replies using the bidirectional long short term memory. So this together is going to help us to model this particular Luma verification task. So here is our approach. First, we'll talk about task formulation. Given a conversational thread of a source post P and a set of reply posts R from R1 up to Rn, where n is the total number of reply posts. So the goal of Luma verification in this context is to classify the source post P into one of three Luma classes, which are true Luma, false Luma, and unverified Luma. So unverified Luma is that type of source post which has not been classified as true or false, or we don't have the required information to classify it as true Luma or false Luma. The necessary information is missing. So all of the Lumas following that category, they are classified as unverified Luma. Additionally, each post is associated with a stance label, whether it is a source post or it is a reply to the source post. So the stance categories are in support, deny, query, and comment. Before I explain the approach in details, let's look at the sample online discourse that we are trying to verify here for Luma. So this is the diagram, and from this diagram, the first post here is the source post, which we are trying to find its Luma veracity. So this post has the Luma label of false, and its stance label is support. And all the posts below this one are reactions to this particular source post. And all the reactions at the same level, it means they are at the same level of reaction to the source post. And it can also be seen from here that a reply can also respond to another reply. So some replies do not respond exactly to the source post, but they respond to the source post indirectly using the intermediate reply post to the source post. And these reply posts have these associated Luma labels to the right here. So we try to leverage all of this information here for our Luma verification task. So we now present the details of our approach, which is subdivided into 3 components. First is post-embedding representation and aggregation. So this task firstly uses BERT to extract contextual embeddings for both the source post and reply post. So if we go to the diagram here, below we have the thread. So when we go to the feature extraction module, we extract the source post and the reply post from this thread. Then we use BERT to create the word embeddings for these posts. Then we send them onto different routes. The source post goes onto a different route here to the right, and up here the reply embeddings go into the post embedding aggregation route. So here every reply embedding is aggregated depending on its label, on its stance label. So for example, all of those embeddings which are for the support stance, they are aggregated together. And all of those which are for the deny stance are aggregated together. So this goes on until all of the stance labels in the conversation thread are taken care of. So this post-embedding concatenation just puts together the source post embedding and the aggregated reply embeddings. The second step is stance-aware sequence encoding. So this uses a bidirectional long short-term memory to encode the sequence of stance labels in a temporal order. So this by LSTM uses this module to the right here. So this kind of encoding, the idea is try us to understand how this change in stance from one reply to another can help us to get the signals which will give cues for the module to determine the veracity of the Luma in the source post. So after these two different modeling approaches, then these features are concatenated here and fed into the last component, which is the unified feed-forward layer. So the fully connected layer is followed by the dropout layer, which is used for regularization to avoid our model overfitting on the instances. And then we have the softmax for calculating the probability. And then lastly, we have the Luma label for this thread down here. Now we present the experiments which were conducted to evaluate our approach. So the table on top is giving the statistics of the datasets. We use 3 datasets. So we have the number of threads in each dataset here. We have the number of tweets for every dataset. For the number of tweets this is adding a source post and the reply post to a source post. And in the middle, we have the stance distribution for every dataset, and lastly, we have the Luma veracity labels distribution for every dataset. As we can see on the film dataset, the last row, there are no stance labels because this dataset has only Luma labels, but it doesn't have stance label for every post in the dataset. So to do this, what we did, to find the stance labels, we used our model, but we removed the reply embedding aggregation by stance label and the by-L-stem modeling of stance evolution from the model. And then we also use smart oversampling technique on the datasets which have labels. So what we did is we use the same eval and Luma eval dataset stance instances. We trained our model on those two datasets with the oversampling technique, since the stance label is skewed towards the comment stance in both of these datasets. And then the resulting model was used to predict the stance labels for the film dataset. Then below we have the baselines, which were used for evaluation against our work. We have the event AI ensemble learning technique. Then secondly, we have long former, which uses multitask learning. So this work does task detection and Luma verification separately. But for the Luma verification, they use only source post without using the replies. Then we have the coupled hierarchical transformer. So this uses the global transformer, but firstly it does it uses the whole conversation thread with the replies. It unrolls it into one vector, divides the vector into sub-portions, encodes every portion with BERT separately depending on the sequence length of BERT. Then the output of BERT encodings, they are fed into the global transformer. Then we have the joint Luma and stance module, which also does stance detection and Luma verification. On Luma verification, they also use on a source post and they leverage the graph transformer. And the SAMGAT, which uses graph attention network, this also does only does only Luma verification. So the far right is the results of experiments and comparisons against these baselines. So we used the macro F1 and accuracy as evaluation metrics, and it can be shown from this table below here to the far right that our model is performing all other techniques on these particular datasets. In addition to comparing with baselines, we also did other two experiments. First is ablation study. We started by removing replies and only used the source post for Luma verification. Then we removed the embedding aggregation. Instead, we unrolled the conversation thread and fed it into BERT. That is, BERT was only used once, and we truncated the conversation thread once it exceeded the sequence length of BERT. And we subsequently removed the stance aware, which uses the by-L-stem encoding of the stance labels. And then we used the whole model, which uses everything. So this table to the far left on top here shows the results of this ablation study. It can be seen that the removal of every component affects the model. And this evaluation was done on only the Luma Eval 2017 and Luma Eval 2019 datasets. And we can see that still the model which uses everything has a stronger performance on these datasets. So this also underscores our proposal that using these features into this model will help in addressing this problem of Luma verification. The second, the other experiment was on error detection. So to assess error detection capabilities, we define detection checkpoints based on the elapsed time spanning 24 hours since the initial post was created on a social media platform. Then at each checkpoint, only replies accumulated up to that point are considered for model evaluation. So here, what we're trying to do is we're trying to see how can we use our model in real life experiences, because we try to see if this model can try to detect these rumors early at the time they are posted. So we do this on the same eval dataset only, and this line graph to the far right on top here is showing the results of error detection, and these results are in macro F1 score. It can be shown that even after 4 hours, our model outperforms every other model on error detection. So which shows that our model can still be applied in real life experiences. Now we discuss the results. So unlike baseline models such as CHT that process hierarchical groups separately, our aggregation strategy preserves stance distribution and reduces information loss, allowing for better contextual reasoning. Again, our model aggregates reply post embeddings grouped by stance type, ensuring that stance conditional representations provide a holistic view of the conversation. And also, aggregation mitigates the sequence length limitation of BERT by summarizing the impact of all replies in a stance-specific manner. And lastly, while baselines implicitly incorporate stance, our work explicitly embeds and encodes stance labels with by L-stem, so which preserves the chronological order of stance evolution, which is critical for understanding how rumors develop over time and allowing it to capture stance progression and interactions. In conclusion, in this work, we introduced a novel stance-conditioned rumor verification model that integrates bed-based source post embeddings and reply post embedding aggregation together with by-L-stem encoding of stance labels in order to enhance the detection of rumors in online discourse. In our experiments, our results show that integrating source post embeddings with aggregated reply features enhances classification performance compared to models that treat them separately. We have also shown that processing stance sequences chronologically using biostem preserves the natural evolution of discussions, leading to more context-aware representations. We have also shown that rumor detection analysis demonstrates that our model achieves faster and more accurate misinformation detection than competing methods. So this underscores its practical utility in real-world rumor detection. Despite the contributions of our work, we also point out some limitations and the direction for future work. First limitation is a heavy reliance on accurate stance annotations that may not always be available or reliable in real-world scenarios. So in other words, most of the data that is posted on social media, it's hard to detect its stance label. And the model is trained and evaluated on datasets that may not fully capture real-world misinformation trends across different social media platforms. So in this context, we only use Reddit and Twitter data, which is now X. So we try to extend this to other social media platforms. The study also focuses exclusively on textual content. So we do not use visual information here like memes, videos, and images. So this might supplement the verification of aroma. So future work could explore weekly supervised and self-supervised learning to reduce reliance on manually labeled stance data, do some cross-platform adaptation to generalize rumor detection across different social media environments such as Threads, TikTok, Facebook. Subsequently, the incorporation of multimodal data, that is text, images, and videos, to enhance rumor verification in diverse contexts. And lastly, we try to explore extra structural dynamics, e.g. stance distribution and hierarchical levels encoding, in addition with attention mechanisms. So that's all I had for this presentation. Thank you for being a wonderful audience.